Welcome to the lecture series of digital electronics. Today we will discuss the multi-level circuits, especially multi-level NAND circuit. Combinational circuits are more frequently constructed with NAND and NOR gate rather than the AND and OR gate. NAND and NOR gate are for common from the hardware point of view, and the reason is that the integrated circuits form availability of the gate. NAND or NOR, both gates are a combinational circuit designing, and it is important to recognize the relationship this exists between the circuit constructed with AND or their equivalents NAND NOR diagram. हम जानते हैं कि कोई भी सर्किट इजी से डिजाइन करना हो तो एंड और फंक्शन यानी कि सम ऑफ प्रोडक्ट टर्म या तो प्रोडक्ट ऑफ सम टर्म में बुलियन फंक्शन से कर सकते हैं। तो सिमिलरली ये जो एंड गेट और गेट दोनों मिला के अगर कोई सर्किट डिजाइन करे तो देयर इज रिक्वायर two different ICs, some AND type gate IC and OR type of gate IC. While if the same thing can be designed and or can be converted into NAND, so only NAND gates are required to complete the design the any combination circuit. And a NAND gate are available only in particular ICs, so there is no required different type of the ICs. So circuit size also reduce and functionality can be easy. The implementation of two-level NAND and NOR logic diagram we will consider here. It is a multi-level circuit because the more than one level NAND gates are utilized to perform the sum of product or product sum term. The NAND gate is to be first universal gate. Why? Because in digital system can be implemented with it. Any digital circuit can be implemented, combinational circuit with it. First reason is that combinational circuit and sequential circuit also can be constructed with the NAND gate. Because the flip-flop can also be designed with the help of two NAND gate connected back to back. Means a NAND gate can be implemented useful to design another logical operation such like as suppose a NAND gate single input tied, so it perform like as an inverter or NOT gate is that. And if the NAND gate output connected here, the NAND gate output AB dash, if I put again like as an inverter, it will become AND gate. And if we take the different input tied and take complement A dash and B dash, this A dash B dash and NANDed, it will become A plus B. So all three basic function NOT, and OR gate can be implemented with the help of NAND circuit, NAND gate. So a convenient way to implement combinational circuit with NAND gate is obtain simplified the Boolean function in terms of AND or NOT, and or NOT operation to NAND operation is usually quite complicated because it involves large number of application of the De Morgan's theorem. And this difficulty can be avoided by the simple circuit manipulation and the simple rules outlined below. So Boolean function implementation rules are there. The implementation Boolean function with NAND gate may be obtained by the means of simple block diagram manipulation technique. This method requires that two other logic diagram are drawn prior to obtain the NAND diagram. And it procedure is very simple, straightforward. First, from the given algebraic expression, draw the logic diagram with the basic gates AND, OR, and NOT, and assume that both the normal and complement inputs are available to use for the particular circuit diagram. Then we have to draw the second diagram, equivalence NAND gate of as per given the previous figure, that we can design AND or a NOT function with the help of NAND gate. Then remove the bubble, cascading bubble. Remove any two cascade inverters from the diagram since double inversion does not perform the logical function. How? Because if I have any input x, first is x dash, and then again it is invert, it will become x. So there is no meaning of this two gate. We can remove it by cancel out. So connected a single external input and complement the corresponding input variable. The new logic diagram obtained is the required NAND gate implementation. Let's take one simple example. Suppose here the implementation circuit f equal to a in bracket b plus this b plus cd. So what we have to do? We have to do cd here and the gate and it ORing with the b, this one, and ended with a. Okay, up to this one function a in bracket b plus c plus d here. This one is b c dash and it's ORing, and finally we obtain the f gate is there. So here we have to convert this into the form of NAND gate. So first what we'll do, this AND gate convert into NAND gate. So NAND followed by NAND gate followed by inverter means second NAND gate. This OR gate require three NAND gate. This AND gate is required two AND gate, two AND gate here, and three OR gate here. So block diagram look like is in this way. First C and D ended. So CD hold here this NAND gate. In the second this OR gate is replaced by this one, three gates. Okay, then the A is ended with the above one. So here again two input different and AND gate is required. So this one, third one, and then ORing with the BC dash. Now AND gate is through cascading NAND gate. OR gate is through first complemented then ended. AND gate to cascading NAND gate, to cascading NAND gate, and OR means complemented then implemented. Now see here. Suppose here the input is x. This is x dash, and this will become x. So we can remove these two gate. Okay, because it's simply function is that we can directly connect this one here. Okay, similarly here this NAND gate can be removed here because the functionality is same and we can directly connect the circuit diagram in this way. Similarly, we can also remove this and this because the x output is x dash output is x. So it is better that thing x is directly connected here. So in this way, here we are removing 1, 2, 3, 4, 5 and 6 gates are there. Okay, so in this way we can convert only 5 gates to obtain the circuit diagram. So the minimum gate is required. Suppose a NAND gate available with the 6 NAND gate in one IC. So don't require the number of gates, number of ICs, integrated circuit. Only one NAND circuit can be easily useful to convert the any logical expression if in form of sum of product or product of sum with the help of NAND gate. The somewhat use the required to draw the block diagram also to find out the equivalence of NAND gate. Now next is that analysis procedure. Suppose here the foregoing procedure is considered the problem of deriving NAND logic diagram. The reverse process is the analysis process, which states that the given NAND logic diagram cumulated with the Boolean expression or a truth table. The analysis of NAND logic diagram follows the same procedure represented analysis of combinational circuit. The only difference is that NAND logic require repeated application of De Morgan's theorem. We shall now demonstrate the derivation of Boolean function from the logic diagram. Then we will follow the derivation of the truth table directly from the NAND logic, and finally a method will be represented for the converting NAND logic diagram to AND OR function by means of block diagram manipulation. So the derivation from the Boolean function first. So here the T1 function is given here. C, D, A, B, C, D, four inputs are there. And so first is that the procedure from the derived Boolean function logic diagram. Procedure demonstrated NAND logic diagram shown in this scheme. So first all outputs labeled with the arbitrary symbols. Like as first we take the arbitrary symbol T1. So T1 is the C dash C D whole dash. So it will become C dash plus D dash. Next is the defined T2. T2 is the input of BC dash NAND gate. So it will become B dash plus C T2 output. Okay. And then T3. T3 is the B1 dash T1 whole dash. B1. T3 is the T1 and B dash. Both are NANDed here. This one. B dash and T1. So B dash T1 whole dash NANDed operation, and T1 we already defined, so it will become B dash C dash plus B dash D dash, and then NAND operation, it will become B plus C and B plus D. T4. T4 is the A T3 dash. So A substitute T3 value B plus CD. So we obtain that A in bracket B plus CD whole dash, while F is equal to T2 into T4 whole dash. So we simplified it. It is in terms of BC dash plus A in bracket B plus CD. This derivation of the T1, T2, T3, T4 put into the flow chart, and a value of the ABCD all the value. So T1, T2, T3, which we derived here in the example, that the T1 is equal to C dash plus D dash. So according to it, C dash plus D dash, if both are, any one is 0, so the result is 1 in this way. If CD is equal to 1, 1, then the result is 0. Okay. Similarly, T2 is the B dash plus C. T2 is B dash plus C. So here B dash plus C, B zeros, obviously B dash is 1, so it will become 1. B dash plus C here is it is 0. Okay. So T2 is B dash plus C. In this way, we can derive. Now put the Carnot map with the help of Carnot map and derive the F equal to AB plus ACD plus BC whole dash. So this is the same expression which we find out the correct answer is that. Okay. So in this way, we can also analyze the NAND circuit is that. It is common, sometimes convenient to convert the NAND logic to a equivalence and or logic diagram, facilitate the analysis process. By doing so, the Boolean function can be derived more easily without the involving or applying De Morgan's theorem. The conversion of logic diagram is accomplished through process reverse from that use implementation. The symbol represented here for the conveniency that the AND or logic form NAND diagram is always equivalent to AND OR form, and the conversion of NAND diagram AND OR diagram is achieved through a changing the symbol of AND invert to invert OR. This is AND invert symbol, and this symbol is known as a invert OR. So meaning is same. Why? Because the A, B, C whole dash, and this is A dash plus B dash plus C dash. So this meaning is same as per the De Morgan, so it will become ABC whole dash. So sometime to reduce the bubbles form, and invert can be converted to the invert or form is that. Let's take one example. Suppose we have to do the analysis of this process. The circuit diagram is given here. So for what we do, first we convert this NAND gate into inverter. Okay, why? So obviously even number to remove the representation of complementation. The one input and or gate can be removed since it does not perform a logical function. A one input and an or circled input changed so that inverter circuit can be replaced. So here, what we do, T3 and T2 is there. So here fine. So this we can convert into the OR invert logic. So this one and this one. NAND is replaced by invert OR gate is there. So here we see that this bubble can be removed. Meaning is same. B dash can be converted to bit. Okay, so the bubble can be removed. Here, this bubble can be also removed. And this bubble will be removed. So, and this AND gate, this will become OR gate, AND gate, and OR gate is that. Okay, in this way. So, we are removed a bubble to back connection, and the in complement they convert also into the form of complement. So finally we obtain that the circuit is in reverse order. It is in form of AND and OR logic is that. Similarly, multi-level NOR circuit is that. The same concept is that, but here instead of AND OR, here OR AND logic is that. So it is known as a product of sum term. Not gate, simply gate is replaced one input, both are tied to each other and given, so it will be a dash. Two NOR gate, it represent one OR gate common because the complement De Morgan's will be removed due to this second inverter NOR gate is that. A dash, B dash, NORing it will become AND gate. So AND and OR logic will be differ, look like a similarly in NAND and NOR. So NOR gate is also universal gate. NOR gate, draw the AND OR logic from the given expression. Assume that the both in normal and complement inputs are there. Draw the second logic diagram, NOR logic, as the function already defined in previously. Remove the cascading inverters, bubbles, which are repeated and give the same single external input. Complement the corresponding input variables. Same like is the NAND logic we applied here. So this is the circuit diagram which already given in the previous case. So AND gate is replaced by first complement and then NOR. The and OR gate is replaced by two cascading or NOR. So AND OR in this way. Okay. Now here, see this NOR and this NOR can be cancelled out because the X directly can be useful here. Similarly here, this NOR gate and okay. Okay, one gate is here, the second gate A dash. So here can be replaced if we put here A dash. Complement is that. So in this way we can reduce. So 1, 2, 3, 4, 5, and 6. That many gates we can reduce, converting complement. The previous two stages are there. And NOR gate is replaced equivalency or invert simple NOR gate or invert AND gate is that. So invert AND gate is it is also known as a NOR gate. Remember that thing. The result is always same like as a NOR gate is that. So conversion of the NOR logic from the AND OR operation. So first what we do, whatever this input here C dash D dash. So first and second circuit we are replaced by the invert AND. Okay, then third next one level this is also replaced by invert and final stage is also replaced by invert AND logic. Now these bubbles can be replaced by one. We can remove the cascading bubbles In similar way, the dash is replaced by bubble. So here C and D convert C dash D dash instead of, and this also be complement. So bubble can be removed to find out the end or information is there. Okay, in this way. So I hope you can understood the things, the implementation of NAND and NOR universal gate. In this way, we can design any circuit, any combinational or sequential circuit. So NAND and NOR gates are known as a universal gate. Have a good day.